In Chapter 4 we're going to be looking at regression. Now regression is kind of the next natural step that we take after Chapter 3, in which we looked at scatter plots and correlation. So the first step when we're talking about regression is to actually come up with a particular line that describes the data. So notice that this does say line, so we are looking at linear models. We're not looking at models that might look more exponential or one that might look more curved. We're only focusing on linear models. How do we actually calculate the least square regression line? And we're going to be relying on Minitab or learning how to use our calculators to come up with this. And then once we find that least square regression line, we'll look at the coefficient of determination, which is r squared. And if you remember from our cricket data that we looked at, we did have a value of r squared on that table in Minitab. Then we'll look at outliers and how these outliers influence the outcome of the line, along with influential observations. We'll look at a line used to make predictions, and we'll also end with association does not imply causation, meaning just because we can come up with a regression line and we can predict doesn't mean it's appropriate for the situation. The first thing we're going to look at is a graph of a scatter plot and the least square regression line. Now before, when we talked about things, we'd kind of sketch in a line, but everybody that would sketch in a line might sketch in one that was a little bit different. So what we're trying to do is we're trying to come up with the best line to describe a particular scatter plot. So mathematically, the least square regression line is the unique line such that the sum of the vertical distances between the data points and the line is 0, and the sum of the squared vertical distance is the smallest possible. Now this is kind of a big definition. I don't expect you to memorize it. I kind of expect you to have a general idea of what's happening here, but this least square regression line is one we actually use calculus to solve and to prove. So if we look at the picture down here, first of all we have a scatter plot that's familiar to us that we've looked at before. On the horizontal axis we have the number of beers. On the vertical axis we have blood alcohol content. Now remember, when we're talking about vertical distances, we're talking about up and down direction. So least squares regression line is talking about taking all these distances from a data point to the line of best fit and making sure that they are the smallest possible distances. Now the only problem with that is that the sum of these distances, for instance, some will be positive if they're above and some will be negative if they're below, they will sum to 0 every single time, and so that's not very helpful. So that's why we talk about the sum of the square distances up here, because we want to square these distances and minimize the squared values. So I could have another line drawn in here, but it wouldn't be the line of best fit because it doesn't minimize the sum of those square distances. And again, I don't expect you to go through and calculate these and come up with the formula, but to understand what formula we're using and why it works. So next thing we want to do is we want to focus in on a particular couple points in this graph and kind of blow it up and see exactly what's going on with those square distances. So let's go ahead and look at these 2 points, and these 2 points are represented here on this graph, and here is our line of best fit, or our regression line. Well, this value right here is 0.07 for our y value. Okay, now if we look over here, that would be associated with 3, the value x equal 3, and that's the same true here. So both of these values have x equal 3 associated with them. So if I looked at this distance, this would be a positive distance, the y value minus y hat. Y hat is this line right here. It's our line of prediction. And I have a distance of 0.032 there because our predicted value, if we plug 3 into our regression equation, would have been 0.048. So when I subtract, I get a positive value. Here, when I take my observation minus y hat, I get a negative value. Now notice these don't sum to 0, but if I did this with every single data point, the overall sum would be 0. Now because I'm going to get 0 every time here, when I talk about these values, I have to square the distances. Now a couple quick things. Because it is the vertical distances that are minimized, the distinction between x and y is crucial in regression. Now remember, when we calculated the correlation coefficient, x and y didn't really matter. But because we're looking at regression equations, knowing the difference between x and y is very important. If you switched the axes, you'd get a different regression line. So what we always want to keep in mind here is always use the response variable for y, and that's our vertical value, and always use our explanatory variable on our x-axis. So again, it's very important that you keep x and y distinct and you know the difference between them. Now when we talk about the least square regression line, I use this notation of y hat. So let's go ahead and talk about some notation that's particular to regression lines. Now a lot of this has to do with working with equations of lines, so it should look pretty familiar. Now y hat is basically used to represent the prediction line. Y hat is the predicted value on the regression line. So again, y hat is a predicted y, oops, I should sneak in a y here, the predicted y value on the regression line. Now what we like to do is to talk about this as the equation of a line. So we look at y hat equals intercept plus the slope times x. So those of you who have worked with algebra quite a bit before and looked at equations of lines, this looks like your y equal mx plus b. M is your slope, b is your y-intercept. Now of course it'd be too easy if we use the same equation, y equal mx plus b, so we change this a little bit in statistics, and to shortcut that we call this y hat equal a plus bx. Now this value of a is the y-intercept, that means where it crosses the y-axis, and this value of b is the slope of that regression line. So let's go ahead and focus in on a little bit more about slope now. When we talk about slope before in algebra, we always had an idea about negative slope. So this has negative slope. So in our case, slope is less than 0 because it's negative. B is slope for us, so we'd say b is less than 0. Now we also can have zero slope. Now zero slope is a horizontal line. Sometimes people think zero slope is a vertical line. That's undefined slope. So in this case we have zero slope. Slope equals 0. And our slope is represented by b, so b equals 0 in this case. So we have negative slope, zero slope, and so our last one must be positive slope here. So again, I have positive slope, so slope is greater than 0. B is our slope, so this is talking about b being positive, greater than 0. Now we are using a and b to represent the y-intercept and slope, but I have to warn you that different pieces of software use different notations. So you might run into some software that might use b here and a here. So you have to look at the context of the problem. Whatever x is being multiplied by, whatever this coefficient is, that's what represents the slope. And then whatever stands alone over here as a constant will always be your y-intercept. So again, you'll see other conventions that you might run across if you're using your TI-89 or if you're using some different type of software. But the basic idea is it's the slope of an equation, or the equation of a line. So let's go ahead and look about, now that we have the notation down, let's look at slope a little bit more. Now I know all of you have worked extensively with slopes of lines in your algebra courses, but let's just do a quick review. So to get started here, we already know what slope is. Slope in its general sense means rise over run. So when we talk about rise over run, we're talking about vertical increase over horizontal increase. And of course this could be a decrease as well, but we're looking at a positive sloping regression line right here. So the slope of the regression line describes how much we expect y to change on average for every unit change in x. So we're increasing by 1 unit here in the x direction, and we're looking at the increases then in y. And what we do is we take each of these increases in y, okay, and these are only the ones below the x-axis, or sorry, below the regression line, and then all these changes as well, and we look at the average of them. So that's what we're talking about with slope. Now the intercept we haven't talked about as much. The intercept is basically where it will cross the y-axis. Now this one looks like it'll cross slightly above 0. It's kind of hard to tell unless we extend it. But the intercept is a necessary mathematical descriptor of the regression line. It doesn't really describe anything in specific about the data. The y-intercept is needed because just with the slope, I don't really have an idea about where this line will cross. I have to know a little bit more information because this line could be moved up here and have the same slope, but it would cross at a different y value. So again, the y-intercept just gives me an idea of not just the slope, but the position of where the line is on the Cartesian coordinate system. Now one other interesting characteristic that we're going to bring up now, and we'll bring up again a little bit later, is there's one point that this line has to go through. So eventually when we look at this data again, x bar and y bar are going to be calculated for each of the data sets for the x values and the y values, and that's kind of a hinge point on this graph. So again, eventually we're going to look at this x bar and y bar, and that will be an important point here. The last thing that we're going to look at about regression lines before we look at actually plotting it is how do we find the equation of that regression line. And again, we're going to rely quite a bit on Minitab to help us out there, or your calculators. So again, as usual, it's important that you either figure out how to use your calculator, or Minitab or Excel would work as well to find your regression lines. So first of all, let's go ahead and look at some equations. Now when we're looking at the least squared regression line, remember B represents the slope of the regression line. So knowing these notations is important. Now the equation that we use to determine what B is R, which is the correlation coefficient, times the standard deviation of the y values divided by the standard deviation of the x values. Now remember, it's important that we distinguish between what x and y are. X is our explanatory variable, y is our response variable. So if we scoot up here real quick and look at that equation again, see, here we are. Look at this equation of this line again. Explanatory was the number of beers, the response variable was blood alcohol content. Now if we switch those around, it'll change the equation of the line. So again, R is the correlation coefficient, S of y is the standard deviation of the response variable y, S of x is the standard deviation of the explanatory variable x. Now the intercept is represented by A, so the intercept of the regression line. A is going to equal y bar minus b x bar. Now of course we have to calculate b first in order to find a, and once I know my value of b, don't over round on it because then that'll make a off a little bit. And I need to find x bar, which is the average of the x's, the averages of the explanatory variable, and the y bar, which is the average of the response variable. Now these formulas are pretty nice. Basically this means that we don't have to calculate all those squared distances to find the least square regression line for a data set. Instead we can rely on these two equations. But typically on your calculators you're going to have to use two variable statistics. So again, a lot of times we looked at one var, one variable. Now we'll be looking at two variable statistics on your calculators or on your Minitab software or Excel. So again, it's important that you get familiar with your calculators and know how to use your calculators to calculate these values for you. Otherwise, you're going to be doing these by hand, and it does take quite a while, and there's a lot of room for error. Now that we know how to calculate a regression line and find its values for the slope and the y-intercept, let's go ahead and look at plotting the regression line. Now we plot the regression line just as we would plot any other line. When we plot a line, the easiest way to plot a line is to know 2 points, because 2 points will define a line. So the easiest way is to use our regression equation to plot 2 points, or to find 2 points, plot the 2 points and connect them, and that will be our line. Now again, the regression line always passes through x bar, y bar. It's an ordered pair. So let's go ahead and pop up our scatter plot that we've been looking at with a regression line drawn in, and then look at our calculated values for our equation. So here's our scatter plot. Here's our least square regression line. Now this has quite a few different characteristics that we want to look at. First of all, our hint here that we've talked about before, the value for x bar and y bar is an ordered pair. And so in this particular case I can calculate x bar somewhere between 4 and 5 it looks like, and y bar, which is somewhere between 0.06 and 0.08, when we can actually calculate this as an ordered pair and plot it. So every single regression line will go through the ordered pair x bar comma y bar. So again, ordered pair. Next thing we do is we look at this prediction equation, and again we are given this, we're not going to worry about calculating it, and it looks like we have y equal m, my slope is 0.0144, x plus our y-intercept is 0.0008. So you can see the importance of not over rounding here. So again, this is my regression equation. Now with this particular regression equation, my slope is the coefficient in front of the x value, so this is my slope. And my y-intercept is very, very close to 0, but not quite. So this is my regression equation. Now what's happening here is we're using this to predict what's going on at a particular value. So here I'm using this to see what's going on with 8. So this would mean if I had 8 beers, what am I predicting my blood alcohol content to be? So I would plug in 8 for x because that's my horizontal variable here, that's my explanatory variable. And when I plug this in, remember order of operations, you do multiplication first and then addition. I get 0.116. So what this is doing is it's saying for people who drink 8 beers, I would predict on average that their blood alcohol content would be 0.116. That's what's happening here. And so this is the plotted point. If you plug in an 8, I hit the line, I come over here, and that's at a height of about 0.116. Now I have another point here at 1. Now I could have chosen 2, 3, 4, 5, 6, 7, any of these points. I just chose 1 and 8 to work with here. So again, plug in a value of 1, and when I use my order of operations here, I get 0.0152. So again, when I plug in 1, on average, a person who has 1 beer, you would expect their blood alcohol content on average to be about 0.0152. So once I know this point and this red point, and I do know it goes through x bar, y bar, I just connect those points and there's my regression equation. Now sometimes the regression equation will actually go through a point of the data set, but that's just coincidental. It's not always going to happen like that. The only point that will always be going through is x bar comma y bar, our ordered pair here. Now least square regression is only used for linear associations. Don't compute the regression line until you have confirmed there's a linear relationship between x and y with a scatter plot. So we want to talk about when is it appropriate to use a least square regression line. Now one of the problems here is that a calculator or a computer will calculate a least square regression line for any set of data. It doesn't distinguish between whether it has a linear model or not, so you have to be really careful about this. So we're going to again note that only use a least square regression line when there's a linear relationship. So first of all, always plot the data. And the reason we want to always plot the data first is we want to look to make sure that a linear association is reasonable. So always plot the data to be sure a linear association is reasonable. If it isn't, then I need to use some other sort of model. But again, in this class we'll be focusing on a model that's always going to be linear. So let's go ahead and look at some data sets and some graphs where I can look to see if that linear assumption is being met. So the data that we're going to look at, I'm going to be looking at 4 graphs from 4 different data sets. So here we have data set A, data set B, C, and D. So we're going to look at 4 different graphs. Now each of these particular data sets, here's our x values and our y values, have exactly the same linear regression equation. So our slope is 0.5, our y-intercept is 3, and of course our prediction line is given by y hat. But again, do I assume that this is the appropriate linear regression equation without looking at a scatter plot? And no, don't report this as a linear regression equation until you've plotted the data. So we want to take each of these data sets and plot them and look at what that linear association is or isn't. So for the first data set A, this is the graph that we have. And it does seem to appear that there is a linear pattern here, but it's not a really super strong linear pattern. But I would say in this particular case there's a moderate linear association. So since there is some sort of linear association here, I would say that regression is okay. Now over here with data set B, this isn't linear at all. There's a nice curve. It's almost like an upside down parabola. So here I would say that there's an obvious nonlinear relationship. So in this particular case, regression, linear regression, is not okay. It's not appropriate. Okay, let's keep looking down here. And data set C, down here, this is very linear. It's perfectly linear, in fact, but this one outlier kind of messes things up. So in this particular case, I have one extreme outlier. It seems like linear associations here seem appropriate, but because of this outlier I'm going to have to look a little bit further. So perhaps linear association is appropriate, or perhaps regression is okay. I need to find out about this outlier and see what's happening. Now in this last data set you might say, well yes, linear association, it's a vertical line. Vertical line has undefined slope, so in this particular case I would just have an equation of, let's say, x equal 5, 6, 7, 8. X equal 8 would be my regression equation, except for this value is an outlier as well. So I only have 2 values of x here, and it looks like to me I need a little bit more data. So more data, more values of x are needed to try and look at any sort of equation right now. So I think I need to redesign my experiment or gather some more data. So in this particular case, only data set A is clearly suitable for linear regression. Data set C is problematic because the outlier is very suspicious. It could be a typo, or maybe it's an experimental error, or maybe it is really a data point in my data set that I'm going to have to work with. But further examination looks to be appropriate. The next thing we want to look at is the coefficient of determination. Now again, with the coefficient of determination, we're going to use Minitab or your calculator to help us figure out what this one is. This is r squared. Now remember, r, your correlation coefficient, this is r squared. It's the square of the correlation coefficient. So once I find the value of r for the correlation coefficient, I can square that to figure out the coefficient of determination. Now basically, r squared represents the fraction of the variance in y that can be explained by the regression model. So it's kind of looking at the reliability of our regression model. So again, a lot of times when we're working here, I believe in Minitab we saw this as a capital R squared. So whether it's a capital R squared or a lowercase r squared, it's still the coefficient of determination. Now there's a lot of formulas that go into calculating this, and I don't really want to focus in on the formulas because we can use the software to come up with these values for us. But your book does go through some extensive formulas and steps to figure out what's going on here. So what I'd like to do is look at a couple of graphs, and then based on these graphs try and come up with the correlation coefficient, the coefficient of determination, and then try and talk about what the correlation coefficient and the coefficient of determination are saying about the particular scatter plot in the data. Now we looked at this data before and we found the correlation coefficient back in the last chapter, and we found that the value of R was 0.87. That was the correlation coefficient. Now remember, the correlation coefficient gives us the strength of the linear relationship between two variables. Now if we square 0.87, we'd get about 0.76. So this is the coefficient of determination. Now from here we need to interpret what that coefficient of determination means. So 0.76 is the same as 76%. So 76% is the number that we're looking at here, and basically this means the model, our regression equation y hat that we were working with, explains 76% of individual variations in our y value, which was blood alcohol content. And that's pretty good. We want this value to be pretty high. We want our line to explain a lot of the variability in our data. So we want r squared to be very high. Now because r is being squared, we'll never get a negative number here. So for r squared, the only values that are possible for r squared are between 0 and 1. So you should never get anything more than 1, and you should never get a negative value for r squared. Next thing I want to look at are some scatter plots, and then based on these scatter plots try and come up with a value for a correlation coefficient, and then based on correlation coefficient, coefficient of determination, and then some interpretation of what that correlation coefficient and coefficient of determination mean. So let's go ahead and look at interpreting what r squared is for some different scatter plots. So for this first scatter plot, we can see that there's a slight negative trend to the data, and our correlation coefficient here shows that it's negative, and 0.3 is its reasonably, somewhat strong linear association between our variables of x and y. Now because our correlation coefficient is negative 0.3, r squared will be positive 0.09, and we usually express it as a percentage. So basically the regression model explains not even 10% of the variations in y. So our regression model is not very good, and the reason it's not very good is that we don't have a very strong association between these two variables. Now for our middle graph here, it does still seem to have a negative correlation, but it's a lot stronger. The points are clustered a lot more tight around this particular regression line. So here our correlation coefficient is still negative, but it's really close to -1, so I have a pretty strong relationship here. So correlation coefficient is negative 0.7. I square that, I'll get 49%. So the regression model explains almost half of the variations in y, which is pretty good. Now this last one will be our best case. I still have that negative value, but when I square it, when I square the negative 0.99, I get almost 98% of the regression model explains the variability in y, and that's really good. So again, R quantifies the strength and the direction of a linear relationship between two quantitative variables, our correlation coefficient. Now R is positive if we have a positive linear relationship, and it's negative for negative linear relationship values. Now the closer R is to 0, the weaker the linear relationship is. Now be aware that R has this particular meaning for linear relationships only. So let's go ahead and summarize all of those values for R, and again R is the correlation coefficient. Now we know that this value of r, and again the strength of the linear relationship, the correlation coefficient, can be influenced by outliers. So let's go ahead and look at outliers and influential points when we're talking about scatter plots, and also when we're talking about regression lines. Now graphically speaking, we have an intuitive idea what an outlier is, and we'll look at a graph here in a little bit to kind of exemplify what an outlier is, but basically it's an observation that lies outside the overall pattern. Now for scatter plots, an outlier is a little bit different. Visually we might not notice it as much, but an influential point or an influential individual we really will notice. And an influential individual is an observation that markedly changes the regression line if it's removed. And again, it's usually a point that's kind of off somewhere by itself. So let's go ahead and look at a scatter plot with the regression equation in it so we can see the difference between an outlier and an influential point. Now in this particular graph, we can see that we have our explanatory variable is the age at which your first words are spoken, and this is age in months, and then a particular adaptive score that we're looking at here on the vertical scale. Now we have 2 points that seem to not be following our pattern here. First of all, this is our regression equation. And from here we can see that this point seems to be quite a distance away from the regression equation, so we call it a large outlier. So it's an outlier, and when we talk about a large residual value, we're talking about it's a long way away from our regression line. So it's an outlier. Now over here, this point is very, very close to the regression line. And even though it's very close to the regression line, it's very influential because it takes the line and it kind of pulls the line right toward it. So it's isolated from the rest of the points, and it could be quite influential into seeing what's happening here. So again, large residuals mean outliers. Influential points basically are talking about points that influence the location or the slope of the regression line. Now since we started talking about the idea of residuals here, let's go ahead and look at residuals a little bit further. Now again, residuals are basically the vertical distance from a point to the actual least square regression line. And if we look at all of the residuals, some are positive and some are negative, they're always summed to 0 by definition. Now because they're always going to sum to 0 by definition, it's not very helpful to look at the sum because again it's always guaranteed to be 0. What does help though is to look at individual residuals. Now again, outliers have unusually large residuals in terms of their absolute value. Some will have positive or negative, but it just means it's a very far distance away from the regression line. Now points that are above the line have a positive residual, and so basically these are points above the line and they're overestimates of what exactly is going on here. So here are the points, and then this line underestimates the actual values. Now if I have points below the line, they're negative residuals, and this line overestimates what's happening there. So again, it's the difference between the predicted and observed, which is our residual. Now a lot of times we like to look at residual plots, and we can get into all sorts of extensive outlooks and conversations on that, but we just really want to focus on, first of all, what a residual is and what it means. So again, residuals help us talk about what an outlier does. Let's go ahead and look at another graph now that kind of brings up the difference between outliers and influential points. So with this graph, we already have talked about, again, this data set, age at first words, and the Giselle adaptive score test. We already looked at this value up here that was an outlier because it had a very large residual. And the black line right here and the solid red and the dashed line are going to be 3 different regression lines that we look at. The red line is our original data set. Now the black line is if we take out our outlier point. If we take out child 19, what's the effect on the line? Now the effect on the line without this outlier is very little. If you notice, the difference between all data and this line is very little. So an outlier typically has very little influence on the regression line. However, if we took out this influential point, because it was clear out on the end here, It's kind of isolated over by itself. If we take out child 18, this influential point, wow, look at the difference between the regression line. It goes from the solid red to the dashed red. It really changes that regression line. Now notice all of these lines go through the point x bar, y bar, and that's a guarantee for every single regression equation. So again, the outlier doesn't really change the line substantially. I mean, it does change a little bit, but it's not all that substantial. So child 18 down here, the influential point really changes that regression equation. So it is a very influential point. Next thing we want to look at are how we use these lines to make predictions. Now when we use these lines to making predictions, we need to be careful about our units, and we need to be careful about what our explanatory and response variables are. And we also have to be really careful about only interpolating or making predictions within the values that we've studied. And this is an important point that we'll summarize also at the end of the lecture. But again, only use the equation for least square regression to predict y for any value of x within the range studied. So we looked at blood alcohol content between 0 and 8 drinks. We don't want to interpolate what's going to happen at 32 drinks. So again, prediction outside the range of extrapolation is called extrapolation. We don't want to do that. We don't want to predict that far beyond the bounds of the data. So let's have a look here at the data set that we've been analyzing, number of beers and blood alcohol content. So again, our x values that we studied ranged from 1 to 8. So we really don't want to do prediction too far beyond that, but we could do predictions with all sorts of things. We could do predictions with 2 beers. This is our prediction line. If we plug in a 2, we would plug into our regression equation to figure out what we get back here, and it looks like we get about 0.03. But again, we could plug in any of these values for prediction. So here at 6.5 beers, we'd plug into our prediction line y hat equal our slope, which was 0.0144 times our x value plus our y-intercept, and I'd get 0.0944. Now if we plot this on our graph, that looks like a very reasonable value. And again, we don't want to go beyond the bounds of the data, because something might be happening up here. Let's say if we go up here to, let's say, 32 beers, our blood alcohol content probably can't go over 100% or a total of 1, but I could get my regression equation to show that. So again, avoid interpolating beyond the bounds of the data. It's always a bad idea because we don't know what's going to happen there. Let's go ahead and look at another data set that we've used before, so we can use some making predictions as well on a different data set. So this one is the manatee data set. So first of all, we're going to look at a scatter plot to see if a linear model is appropriate, and then once we've determined that, we could look at a correlation coefficient, a coefficient of determination, and a regression equation. Now again, in this data set we need to look at quite a few different things, and we have looked at this data before, so we have some familiarity with it. But basically here on our horizontal axis, our explanatory variable is the number of powerboats registered in Florida, and of course we take this number times 1,000, so this would be 400,000, 600,000. And then on our vertical scale we have the number of manatee deaths. So R squared here is 0.9061. That's very, very high. It's saying about 91% of the variability in the data can be explained by this regression line, so it does a very good job of prediction. We can also see that the correlation coefficient here would be positive. Now if we wanted to figure out what the correlation coefficient was, we would just take the square root of R squared. This is our prediction equation. The slope is 0.1301, and the y-intercept is a negative 43.7. And you might extend this line and say, well, it's not negative, it looks like it's going to cross right at 1. But remember, our scales here don't go from 0 and 0 on the x as well. So again, the y-intercept doesn't have a lot of meaning here. It wouldn't make sense for there to be negative 43.7 manatee deaths if there were no boats registered. So okay, when we talk about our prediction equation, we could talk about what's happening if we were to limit the number of boat registrations to 500,000 in Florida. Well, here's 500,000 on our x-axis, And so for our y-axis, it looks like we could predict that there'd be, about 20 manatee deaths. But let's actually go ahead and plug it into our prediction equation, and we can see that it's actually a little bit closer to 21.35. So that's why we actually want to use that regression equation as opposed to just kind of eyeballing it on the graph. Quick question, could we use this regression equation to predict the number of manatee deaths with 200,000 powerboat registrations? And the answer is no, we shouldn't, because it's not within the range of our data collection. Our data collection was between 447, it looks like here, and 1,024 times 1,000, of course, powerboat registrations. So when we talk about this, the number of powerboat registrations and the number of manatee deaths due to collision with powerboats in Florida each year for the past 3 decades is being represented. Beware that the data on powerboats are presented in thousands of registrations, so 500,000 powerboat registrations corresponds to 500 on our data set. And we should not use this regression model to predict the number of manatee deaths for, let's say, 200,000 powerboat registrations, because this would predict outside the range of our data, and that's called extrapolation, and we don't want to extrapolate. In this case, extrapolation gives a nonsense prediction of negative deaths. Okay, and that definitely wouldn't make sense. So the next thing we want to do is talk about how association does not imply causation, and that's one of the huge takeaway points from this particular lecture. So again, association does not imply causation. So what does that mean? Well, association means one is related to the other. It doesn't show, however, that one causes the other. Association doesn't matter how strong it is. If our correlation coefficient was 0.99, it does not imply causation. The observed association could have some other cause that we're not looking at. There's also other types of variables that could be attributed to this type of causation. There could be a lurking variable, and we could also talk about confounding variables. So again, the other types of variables that we're looking at, one is a lurking variable, and basically it's a variable that might be out there that we're not studying but would have a big influence or have basically a reason to explain what's going on with a particular study. So again, you have to be careful of lurking variables. Now, we can say that two variables are confounded when their effects on a response variable cannot be distinguished from each other. So for instance, I might have two things that are explaining the response, and I'm only looking at one of them, or one might mask the other. So those are some other things that we need to be careful of. So to summarize, only careful experimentation can show causation, just not a number that we come up with our calculators or Minitab. Now when we talk about confounding variables, they could either be explanatory variables or they could be lurking variables. So those are some important things to keep in mind as well. And we'll talk about some of these as we get further on in some other sections. So let's go ahead and look at some graphs where we're talking about lurking variables to kind of give an idea of what we're looking at here. Now sometimes it's hard to determine what lurking variables are because a lot of times we don't study them. So for our first example, let's go ahead and look at some graphs. So for this first graph, we can clearly see that there looks to be a pretty strong linear association between these two variables. And the variable on our x-axis is shoe size, it's our explanatory variable, and the y-axis variable is a reading index score. So graphically and numerically, mathematically, there seems to be a strong positive association between a child's shoe size and their reading skills. But that doesn't really even make sense. What the lurking variable here is probably age, because as a child grows, their shoe size grows, and also as a child gets older, they get better and better reading skills. So again, child age is most likely the lurking variable here. As kids grow, their feet get bigger and their reading skills improve with practice and of course going to school. Let's go ahead and look at our middle one here. We have a strong positive association between the number of firefighters at a fire site and the amount of damage a fire does. So would we say that the more firefighters there at a site, the more damage there is? And usually not. So what we would talk about here are the more firefighters that are there, the worse the fire, and therefore the worse the fire, the more damage there is. So extent of the fire here is probably a lurking variable. And another thing could be site conditions. You know, maybe it's a difficult fire to fight, so more people have to show up and more damage is done. The last one we're looking at here is a negative association between moderate amounts of wine drinking and death rates from heart disease in developed nations. So from here we can think of a long list of possible lurking variables: diet type, socialization, stress, general quality of life, basic health to begin with, but nothing as obvious as in the other two examples shows up here. So there's a lot of possible lurking variables here. So we talked about diet type, socialization, stress, general quality of life, etc. So again, there's a lot of different possibilities here. The last thing we want to do is, if association does not establish causation, how do we establish causation? Well, establishing causation is actually quite difficult. We can try and establish causation when we have a certain number of characteristics present. First of all, there has to be some sort of a strong association. We're looking at linear associations, but it could be some other type. It could be some pattern that's easily predictable, not just by a line. Also, the association is consistent across all of the data points. Now, higher doses are associated with stronger responses. That would make sense. And also the alleged cause precedes the effect, and the alleged cause is plausible. So those are some things that should be in place, and we can look at this particular to smoking. Now, lung cancer is clearly associated with smoking. Now, this has been established over many years. There's some sort of a relationship here. Now, some people might argue about the strength of the relationship, but there is some sort of an association. Let's say there could be some sort of a genetic mutation that cause people to both get lung cancer and become addicted to smoking. Well, this has been studied as well, but clearly there's not a genetic mutation that causes this. So the lurking variable here would be this genetic mutation, and the genetic mutation would cause two things: lung cancer and addiction to smoking. Now, as it says down here, it took years of research to establish the causation relationship between smoking and lung cancer, but it's been clearly established. Now, you have to be careful about this. Just a few years ago there was talking about global warming and the causation and the prediction of what's going to be happening in 100 years. Now, that can't be clearly established yet. Some people say yes, it's a done deal, we have global warming, and some people say not. So, what is clearly established, what isn't, that is clearly up for discussion. This will be the fourth chapter that we've covered, and it will be chapters 1 through 4 that's covered on the next exam. And in class, we will probably be looking at not only Minitab, but some Excel, and also learning how to use your calculators to come up with these values for our regression equations, so our slope and our y-intercept, and then also using these for prediction. So make sure that you try and use Minitab for these, or Excel, and definitely learn how to use your calculator to find these values.